decades, we believed we understood the universe. We built equations, we launched telescopes, we mapped galaxies, we predicted how everything should behave. And for a while, it all made sense, until it didn't. Because recently something started happening. The universe stopped following our rules. What if our models are wrong? Not slightly wrong, not needs adjustment wrong, completely wrong. For over a century, physics has been built on two pillars: general relativity, which explains gravity and the large-scale universe; quantum mechanics, which explains the tiny world of particles. Both work incredibly well. Too well. We can predict black holes, we can predict gravitational waves, we can predict the behavior of atoms with insane precision. But here's the problem. When we look deeper into space, the universe starts breaking the script. Galaxies rotate too fast. The expansion of the universe is accelerating. Massive structures appear earlier than they should. Entire galactic formations exist where our equations say they shouldn't. And the more powerful our telescopes become, the stranger it gets. The James Webb Space Telescope recently looked further back in time than ever before. And what it saw shocked astronomers. Fully formed galaxies, massive, complex, existing only a few 100 million years after the Big Bang. According to our models, that shouldn't be possible. There wasn't enough time. Matter shouldn't have clumped that fast. Stars shouldn't have formed that quickly. Yet there they were, bright, massive, real. So now scientists are facing an uncomfortable possibility. Maybe the timeline is wrong. Maybe dark matter doesn't behave the way we think. Maybe dark energy isn't what we think it is. Or maybe our entire understanding of cosmic evolution is incomplete. And it's not just early galaxies. There's the Hubble tension. Two different methods of measuring the expansion rate of the universe give two different answers. Not slightly different, significantly different. One of them has to be wrong, or our model of the universe is missing something fundamental. Imagine building a map of reality, and then discovering entire continents that weren't supposed to exist. That's where cosmology is right now, standing at the edge of something we don't fully understand, because every time we improve our instruments, the universe doesn't become clearer, it becomes stranger. And that's dangerous, not physically, but intellectually, because when your best equations stop matching reality, you're not tweaking numbers anymore, you're rewriting foundations. And rewriting the foundations of physics changes everything. So what exactly are these impossible discoveries? What are the specific observations forcing scientists to reconsider decades of theory? And how deep does the problem go? Then, we might be living in a universe far more mysterious than we ever imagined. Let's start with the one that shook cosmology the hardest, the early galaxies. When the James Webb Space Telescope began sending data back, astronomers expected to see faint, small, primitive galaxies forming slowly after the Big Bang. Instead, they saw giants, massive structured galaxies existing just 300 to 500 million years after the beginning of the universe. That's cosmic infancy. According to our standard model, lambda CDM, galaxies need time. Gravity slowly pulls matter together, stars ignite, structures merge, growth takes billions of years. But JWST found galaxies that look mature, too mature. It's like finding a fully grown adult in a kindergarten classroom. Something about the timeline doesn't add up. Either galaxies form much faster than we thought, or the early universe wasn't what we think it was. And that's just the beginning. Now let's talk about something called the Hubble tension. This one is subtle, but terrifying for physicists. There are two main ways to measure how fast the universe is expanding. One looks at nearby galaxies, the other looks at the early universe, using the cosmic microwave background. Both methods are extremely precise, both use solid physics. Both should give the same answer. They don't. The numbers disagree, not by a rounding error, by enough that it can't be ignored. It's like using two perfectly calibrated thermometers and getting two different temperatures for the same room. So what does that mean? It means either we're misunderstanding how expansion works, or there's something affecting the universe that we haven't accounted for. Maybe dark energy changes over time, maybe there's a new particle, maybe gravity behaves differently on cosmic scales. And speaking of gravity, let's talk about dark matter. Galaxies rotate too fast. Stars at the edges move as if there's extra invisible mass holding everything together. We call it dark matter. But here's the uncomfortable truth. We've never directly detected it. Decades of experiments, underground detectors, particle colliders, nothing, zero confirmed detection. So now some physicists are asking a radical question. What if dark matter doesn't exist? What if gravity itself behaves differently at large scales? There's an alternative idea called MOND, modified Newtonian dynamics. It suggests that maybe our equation for gravity needs adjusting. And if gravity is slightly different than we think, that changes everything. Black holes, galaxy formation, cosmic evolution, even the fate of the universe. And then there's dark energy, the force driving the accelerated expansion of the universe. It makes up about 70% of the cosmos, and we have no idea what it is. Think about that. 70% of reality is something we can't explain. We just label it dark energy, as if naming the mystery solves it. So right now, cosmology is in a strange place. Our model works beautifully in many cases, but in the most extreme early and large-scale environments, it starts to wobble. And when multiple cracks appear at the same time, scientists start to wonder, is this a minor patch, or are we approaching a paradigm shift? Because history shows something interesting. Whenever physics breaks, revolution follows. Newton broke, Einstein replaced him, Einstein broke, quantum mechanics emerged. So the real question isn't whether our models are wrong, it's how wrong they are. Every time physics has broken in the past, it felt like the end of certainty. When Newton's laws failed to explain Mercury's orbit, it wasn't just a small correction. It led to Einstein. And Einstein didn't just fix gravity, he reshaped space and time. Then quantum mechanics arrived and shattered reality at the smallest scales. Particles that exist in multiple states, entanglement across vast distances, probability replacing certainty. Each time our models cracked, the universe became stranger, not simpler. So what happens if our current model, the standard model of cosmology, is the next to fall? There are already whispers of what might replace it. Some physicists believe gravity isn't fundamental. They think it might be emergent, not a force, but a byproduct of deeper quantum information. That would mean space-time itself isn't fundamental. It's constructed, like pixels forming an image. Others suggest dark energy may not be constant. Maybe it evolves. Maybe it's interacting with something beyond our current understanding. And then there are the radical ideas. Extra dimensions, hidden forces, new fundamental particles, a modification to general relativity itself. Imagine rewriting Einstein. Imagine discovering that the curvature of space-time is only part of the story, that there's a deeper layer beneath reality. But here's the most unsettling possibility. What if the reason our models are failing is because we're missing a fundamental rule, something as revolutionary as relativity once was, something that makes dark matter unnecessary, explains early galaxies naturally, resolves the Hubble tension, and connects quantum mechanics with gravity? That would be the holy grail, a unified theory, a new framework, a new map of reality. Because right now, physics feels like it did in the early 1900s, confident on the surface, confused underneath. And that's exciting, but it's also humbling, because it reminds us of something powerful. We don't understand the universe as well as we thought, and maybe that's the point. Every generation believes it has nearly solved reality. Every generation is wrong. The universe is not obligated to make sense to us. It only reveals what we are capable of discovering. And right now, it's revealing cracks. Cracks in dark matter, cracks in expansion, cracks in cosmic evolution, and cracks in our confidence. The question is no longer, are our models wrong? The real question is, are we ready for what replaces them? Because when the next revolution in physics arrives, it won't just change textbooks. It will change how we see existence itself. And if history is any guide, the next Einstein may already be alive, working quietly, waiting to show us that everything we thought we knew was only the beginning. For more curiosities and mysteries of the universe, like and subscribe to the channel.